So today we're starting probability, and I'm going to kind of just do some stuff in class today, and then actually go back to definitions of it. Like we're just going to do some probability stuff. To start with, I've got a die. I think I'm going to be fine with everything that I do in class. Like, obviously they can't see me roll the die, but I think they're going to talk in the video. If I start doing something that looks like I need to be showing it on there, just kind of stop me. But I'm going to try to purposely not do that. Alright, so I'm going to roll a die, and you want to win. So on your paper, so like we're going to be doing a lot of stuff like this. This is going to be like within your notes. So on your paper, write down what you think it's going to be. So write down what you think the next roll is going to be. Alright, now write down beside of that the chance that you think you have of getting that. Alright, so I'm rolling my die. Shouldn't have got so aggressive. It was a 2. Raise your hand if you thought it was going to be a 2. Alright, so they thought it was going to be a 2, so they would have won. Nobody else does. What was your probability? People got a 2. What did you think the probability was going to be?
1 out of 6.
1 out of 6, right? What is the proportion of the times that it was a 2? 100%. What was the percent of time it was anything else that you thought it was?
0%.
0. So does that mean you were wrong initially? Does that mean your guess of the probability was wrong? So what does it mean?
You need more trials.
You need more. Okay. Let's roll it a couple more times. Got an order I want to go with. Okay, I'm going to roll it 5 more times. So wait, our first one was a 2. Now it's a 2. One. Six. What is just not being so aggressive? It's a 2. Last one. 6. Alright, so how many of them, what proportion of them were a 2? Half. What proportion of them were 1? 1/6. What proportion of them were 6? 1/3. And what proportion of them were anything else? 0. So, right or wrong? Did it get closer to what you thought it was going to be? So, when you say more, how many do you think I need?
A lot.
A whole lot. Do you think there's all of a sudden going to be one number where it's like, that's not enough? Okay, now it's enough. No, so it's like, you need a whole lot, but we don't know, we don't have a definite number for what a lot is. Let's go ahead and switch into this. So I'm going to do something with a coin. So now we're going to do a coin flip. And I do want you to write this with me. We're going to draw a graph of a coin flip. And let's say we want to do it as percent that are tails. Because if I should have coin ready. Alright, so I've got a coin. And it is heads. So on flip number 1, what is my percentage of tails? So what does this need to be out of? 100. So there's 50, there's 100. You're probably going to want a couple more notches than that. So I'll flip it again. Tails. That's a weird quarter. So now on flip number 2, what is my percentage of tails? Tails. So on my third flip, what's my proportion of tails? Like 2/3-ish here. Tails. So now what is it? 75. So we're going to be connecting these lines. You can go ahead and do it while we're going. Tails. So now we're at 80 something. Oh, we're at 8 or 5. Sorry. That's terrible. Try not to mess it up. Heads. So now we're at what? We've got 6. So that's back to my 2/3 where we were here, right? My spacing should be a little bit better. Y'all might have to help me here. So now how many I might need to keep up with? Number of tails. Number of flips. Oh, well, down there we're doing number of flips. So right now, I just got tails. So this is I had 1, 2, 3, 4. This is 5th tail. So what's 5 out of 7? Oh, I'm 4. Well, yeah, 5. 5 and 2, yeah. So on my 5th here, 5 out of 7 is what?
71.
I'm going to do it just a 10 and we'll stop there. So now we got heads. So now we're 5 out of 8, which is what? Do I go up or down from there? Down a little bit. Heads. So now we're at 5 out of 9, so we're about here. Our last one ended up being tails, which ends up being at what? I mean heads, sorry. I said it wrong. It's the heads. So what happened when I did this in general?
It went back. It went like normalized over time.
So is 10 very much?
No.
No. Did mine happen to get right back to where we expected it to? Yeah. Is that probably going to happen very often? Probably not. Let me see if I can find some. So. So this is the same thing we did. It's just doing it with time. And they did it 15 tosses. So let's say I change that a lot. Do you still see the same concept that we were doing on the board? So is 200 a lot more than 10? Yes. So what starts to happen? It starts to even out. Every time I do this, it's going to be a little bit different. It's like this one started really low. It hadn't even made it to 0.5 yet. But regardless, when I get to higher numbers like 200, what's it always going to do? It's going to start to flatten out. Where is it going to start to flatten out? Where we expected it to. So if we had done this with this example, if we played this for a really long time, would yours end up flattening out about where you expected it to? Yes, but we didn't do it but 6 times, so it just hasn't gotten there yet.
Where would it have flattened out?
What do you mean?
We did that one. Where would it have flattened out?
It would have flattened out at 1/6. Is that what you're asking?
Yeah.
Yeah. But we just don't know. Vertically, it would have flattened out at 1/6. Horizontally, we don't know where exactly the flatten out part would be. All right, so let's go ahead and write some words of what we just did. So our first vocab is going to be an event. No, let's start with sample phrase. How did you know that the probability of that rolling the die was going to be 1/6? Because there were 6. It's a 6-sided die, so you essentially know all of the what? All of the possible outcomes. So your sample space is the set of all possible outcomes. And we always denote it with a capital S. So for our dice example, we would write capital S equals, and then you do brackets, and you literally list out what your outcomes would be. So capital S equals means sample space, and you're listing out all of the possible outcomes. All right, so our next vocab is an event. What did I have you do with the dice example? You wrote down your prediction of what? So you wanted your prediction of what you thought it was going to land on. So this is called an event. How can I relate what you picked, what you thought it would be versus sample space? Which possible outcome you selected. So that's an event. Any outcome. Now, if I said we're playing for a game or playing for points or playing for money or something, I still wouldn't say that because we're in school. Maybe points or candy or something. But if I told you, write down what you think is going to happen, whoever's occurs the most wins. Can you think of how you can be smarter here? Can you know what it's going to land on? No. But can you be smarter with the wording that I just told you? Well, definitely don't pick something that's not in there. Come on, y'all are smart kids. You can figure this out. What do you think it's going to land on?
A number 1, 2, 6.
So a number that is less than 7. Did I tell you couldn't do that? No. So an event is any outcome or a set of outcomes. Even numbers, odd numbers, numbers less than 3, multiples of 2. It is a subset of the sample space. Events are denoted with any capital letter. I'm sure I use any capital letter. Now, you're not going to want to use S, obviously, because that one means something. Typically, we see them as like event E, event A, or event X. Those are ones that are used most often. But eventually you'll want to do ones that like make sense with what you're dealing with. So if like you're talking about odds, you might put O. So example here, let E be even numbers. What would be in the set of that event for a die? 2, 4, 6. So your event that you chose would be whatever number you thought was going to come up. Do you want you to write this with me? I'm going to put something there, obviously. So this goes based off of the different graphs that we just showed. Chance behavior is what in the short run? What is the next roll on the die going to be? Can you tell me with confidence? No. So it is what in the short run? Unpredictable. It is unpredictable because it is a random process. It is unpredictable in the short run, but it has a what kind of pattern in the long run? Predictable. So we don't know what it's going to do on the exact next one, but in the end, it's going to end up flattening out, and that part is predictable. And you will end up being asked a lot of questions about that one statement right there with like homework and context and stuff. Basically saying this in context. We'll talk about a little bit more. All right, so one thing, this concept is called law of large numbers. The name itself kind of throws things off a little bit. It's not that your numbers have to be, the numbers you're choosing have to be big. What has to happen for it to do this? When does it flatten out? When I've done the trial a lot of times. So not that the numbers were big, but that I've done the trial a lot of times. As you observe more and more repetitions of a chance process, the proportion of times the specific outcome reaches a single value. Approaches. So it's saying the exact same thing that we just said above, but in different words. But you will hear within our class law of large numbers mentioned a lot, or mentioned here and there. So I wanted to make sure that you know by definition what it is. Alright, so we've got another scenario, but I soon learned that dice in a glass container is really annoyingly loud, so I'm going to try to do it in a small one. Okay. So there are dice in here. Your options are red, green, and blue. So, just like we did with the dice, write down what you think it's going to be. What's the second question I asked you to do with the dice? Guess the probability. Can you guess the probability here?
How many are there?
No. So you can't guess at all right now. So sometimes it occurs, and this is more of how things really happen. In most of the probability beyond like what we do in high school, kind of. All right, so I'm gonna mix it up. I don't want to show everything. It's red. Alright, so let's go right now. Write down, remember, red, blue, green. Write down red, blue, green, and we're going to tally. Alright, this is kind of talking ahead a little bit right now, but we're trying to guess, or we're trying to find out what the probability is in here, but we don't know. I just got a red. Everybody's good with that, right? Is anybody dead set with, they're all red now? Is anybody convinced by that? No. Alright. Kind of tying in last chapter and kind of thinking ahead. What do I need to do before I draw again? What?
Put that back in.
Put this back in. Because if I don't put this back in, is it going to work with finding the probability of this whole thing? Okay. So, with replacement, without replacement becomes a big conversation. So mix it up. Blue. We got one red, one blue. Put it back. Mix it up. Blue. Blue. On to 6, and then we have a conversation. Red. Blue. How many is that? 5? Okay, so what do we have right now?
2 red and 1 blue.
2 red, 4 blue. So at this point right now, is this a very big sample? No. But if you had to guess right now what percent is blue, would you want to just make up a number on your own? Would it be better to use what we have? So as of right now, our class guess for what percent is blue would be what? 2/3. What percent is green? 0. Alright, so let's go a couple more. Blue. Green. Where does the container go? Red. How many is that? Just 8. Green. So I guess 10.
Yeah.
Alright, so at this point, what percent do we think are blue? 50. What percent do we think are red? 30. What percent do we think are green? 20. Do you see how I can keep doing this over and over until we get a good guess? In real world, this is how a lot of things happen. What's really important is the thing you guys told me at the beginning. I don't know what's in here. How am I picking from what's in here? Randomly. I'm mixing it up. I'm making sure they get replaced. So finding like the probability of, this even works with, proportion of something who are vaccinated or something. They could collect that data. That data is easier to collect because it has to go through a process, but they can continually take samples and use that sample to have a pretty good guess for what the population is. So like this is how it really works all the time. This is called a simulation to try to determine probabilities. So we just did a simulation. The one you picked, the color you picked, based off of what we think they were, the 50, 30, 20. If this were a game, you now have an option. Okay, we're gonna draw one more time for money, and that's win or lose. Would you be better off choosing the one you initially chose, or saying you want to go now with the probability that the one you initially chose does not get picked? So if you chose green, would you rather stick with green or go with anything but green? Anything but green. What about red? Anything but red. What about blue? Does it matter? Because it's what? 50-50. 50-50. Doesn't matter which side you're on. I don't even remember what they actually were. I had 6 blue, 2 green, and 4 red. How close were we to that? Were we exactly?
Also, yeah.
Pretty close. Oh, you were 10.
One red went to the.
That was pretty close for a small sample. If we did it every single time like that, would it be exactly like that? No. I should have done it 2 more times. I should have done 2 more times because it was red. Oh, just for fun. See how different we were from what it actually is. Blue. Oh. Red. Does that get us exact?
Yeah.
I could literally never do this again. I've done it with both of them today. Usually I'm way off. I'm gonna play the lottery or something. I really won't though. Yeah, I'm terrible at gambling. Because I understand the math behind it, so it drives me insane. Somebody actually handed me money one time and said, "Here, go gamble this," and I handed it to somebody else and said, "I'll watch you." Like, I can't do it. It drives me insane. Okay, so I want to add one definition at this point. Do you see any issues with what I just wrote?
It's spelled different.
It is not spelled, and for the first time I actually know how to spell this, and I'm spelling it this way on purpose. Usually I just can't spell. So this is with an E and not with an I. Compliment with an I is like, I think you look nice today, right? This compliment is, your shoes really compliment your outfit. And you've probably, like, everybody knows what I say when your shoes really compliment your outfit, right? Like, you've heard that before. But thinking about what it actually means is, what is your outfit without your shoes? So what happens when I add the shoes to the outfit? It makes it better. It makes it what? Makes it complete. So how does me saying that relate to anything I just said in the last 4 minutes? So your shoes really compliment your outfit, which means without that, they were missing. So what about the things that I just asked you about choosing what choice you want to make for what one's going to win next dealt with the compliment? At the very end, I gave you 2 options. You could either choose what or what. What you wrote down initially, or what? Or anything other. That is compliment. So that is everything that's left. So what is the complement of odd numbers? Rolling a die. Even numbers. What is the complement of rolling a 1? Rolling anything but a 1. So mathematically, how would I always find the probability of the complement? From 100 or from 1. 100% or from 1 if I'm doing with decimals. So complement is everything in the sample space that is not the event. It's in the event. That's weird. So the capital P parentheses means what? Probability of. So this little superscript C means complement. So just based off of what I told you, and not even getting into the fact that we haven't started chapter 5 at all, what would I write P parentheses AC equals after what you just told me? 1 minus, not the whole A, but probability of A. So what's the probability that I roll a 1? 1 out of 6. So what's the complement of that? 5 out of 6. So complement works just how you think it would.
I don't get the PA.
Capital P parentheses just means probability of. So this is saying this is saying probability that it's a 1. This is saying probability that it's not a 1. The C just means complement.
Right, and why do we do 1 minus?
Everything, but I'm going to draw it and let's see if that helps. Okay, so
I got you.
I want you to draw with this a very basic So this circle represents our event, which I called it A over here, so I'm going to call it A. So anything here is the complement. So shaded is the complement. Now that doesn't mean if I draw something like this it needs to be shaded. That's just showing you which part of it is the complement. So this circle represents my event. If my circle represents my event, what does my rectangle represent? Which is what we're okay. Sample space.
Is it remaining sample space?
No. Everything has to be included in the rectangle. Everything has to be included in the sample space. So what's not in my event is everything in the sample space that's not in my event. All right, I want to write some probability rules. What can a probability not be? Negative. What else can a probability not be? Over 100%. And what is 50% as a fraction or decimal? So what is 100% as a fraction or decimal? So all probabilities are between 0 and 1. Can it be 0? Can it be 1? Yes. If the probability of my event is 0, what does that mean?
0%.
So that means it can't what?
Ever.
Can't ever happen. Probability that I pulled out a purple dye out of that sample would be 0. Probability that my dye is not white would be 1. Don't write what I'm writing. Our example with rolling a die, what are my different outcomes? Oh, my pen has been working. What is my probability of each outcome? Everybody's good with that, right? What if I tell you some other scenario? And you don't even know what my scenario is. What's the probability that it's yellow? Why? So you're doing math there. So you're telling me what always has to happen. So when I add up all these, it always has to be 1. So add them up. What is that symbol? What am I adding up? All my probabilities. And every time I add up all my probabilities, it has to equal 1.
Where's that side by side thing?
Sum up out of all of them. This is not a probability rule, but I always have people have issues with it. Yeah, no, I don't want to write that there. Some people write complementary, the 1 minus p thing there. Some people write, like if you look it up in the book, it'll also say a rule is 0 means it can't ever happen. 1 means it's definite to happen. I don't think that's necessary to write down a separate thing. I think y'all can know that much. Okay, so I'm going to give you some examples now and see if you can figure out probability. So let's say we're starting out with our sample space is going to be rolling a die. So I'm going to use that example again. Question number 1 is this. Question number 2 is this. Write that down. What is my answer? The first one. 1/3. Alright. Most of you can look at that and be like, I'm not even in statistics class, I don't care. That's 1/3. I feel good about that, right? So let's think backwards here. Because I'm going to want to figure out what this means in general, in math-wise. So I've got probability 1 as one event. I've got probability 2 as another event. What is the probability that it's 1? What is the probability that it's 2? So what do you think this or means? That makes sense, right? So probability that's odd or even, because probability that's odd is 1/2. Agree with that, right? I don't want you to do this, but theoretically, technically, if it were something like you didn't know what it was, I could also write this out by doing, I could write my event on top. So on the bottom is my sample space. And sometimes this helps for people just to see it because when they're thinking through other things, like this makes sense. So those are all of my options. Now, in order to satisfy this requirement, which ones are? Of these 6, which would satisfy this requirement? Right? So how many options are on top? How many are on bottom? Which is the same thing we did, just a different thought process, right? Same thing here would end up being 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4, 5, 6. 6 out of 6 gives me 1. All right, so the next 2 Now do those. Questions, comments, concerns?
Odd or less than 3, can it be less than 82? Or
No, just less than.
should it include 3? But it's odd.
Right.
Should we include it because it's odd?
That's the part I want to talk about, yeah. Yeah. What is the answer to the first one?
2/3.
Did everybody say 2/3? Did you use this? So now what? So if we just said finding probability of 1 or 3 or finding probability of odd or even, we just take the separate ones and add them. What's an issue here? What's the probability that it's odd? 50%, half. 3 out of 6. What's the probability that it's less than 3? Is that our answer? So where is the issue? One of them is overlapping, so it is in both. So if I wrote it out the way I ended that last one, which I don't want you to write, thinking through the process, I would do this and go through and say, is 1 one of those? Yes. Is 2 one of those? Is 3? Is 4? Is 5?
Yes.
Is 6? How many did I end with on top? How many did I end with on bottom? And this can make sense, but what happens if I'm all of a sudden dealing with like 120 numbers? Am I going to want to go through it like this? No. So let's go back to the way we did that last one. So we started with probability of my first thing plus probability of my second thing. So what is the probability that it's odd? Let's not reduce yet because it's easier to do the same denominator.
1, 2, 3.
What's the probability that it's less than 3? But what is my answer? So,
Why do you get 4?
because what we just did.
Blah.
Odd, less than 2, or less than 3, odd, 4 of them out of the 6 are. So, this gives me 5, so obviously mathematically I need to do what? So, why?
That's the probability of both of them occurring.
So, probability that it is odd and less than 3. So, why did I not have to subtract here?
There are no overlapping.
Because probability of 0 and a 3 is what? 0. They aren't overlapping, so the and part is 0. So this would be probability of multiple of 3 plus probability of multiple of 2 minus probability of multiple of 3 and multiple of 2. So how many of them are multiple of 3?
3.
How many of them are multiple of 2?
3.
How How many of them are both?
One.
So my answer is
Should be 1 and 3 multiples of 3, 1 and 2.
say it again.
1 and 3 multiples of 3, and 1 and 2.
Oh, yeah.
The ones overlap.
Multiples of 3 are 3 and 6. Multiples of so your factors. Multiples, not factors. All right, so we need to talk about two separate things here first. Is we said this group that this group did not. They overlapped. So if I draw this like I drew complement. So in my complement example, the circle represented what? A what? One word. The circle represented an event. How many events do I have? 2. So I'm going to have a box still, because it's still a sample space, but now I have 2 circles. So what will these circles do that these circles will not? Overlap. So these examples do this, as opposed to these examples do not overlap. This is called mutually exclusive. And people always get the term mixed up. The only dumb thing I can think of to help you remember is if you and whoever you are dating have mutually decided that you two are going to be exclusive, are you going to overlap and date with other people? No. So this one, they are not overlapping and dating with other people. Here they are. So we have decided to be exclusive, which means we're not overlapping with other people. And so this one is just called not mutually exclusive. So anytime we are finding probability of A or B, now we have 2 things. We have those 2 options mathematically. Does anybody know what these are called? This one looks like a what letter? U. This is called the what of 2? This is the union. This one is the intersection. We're not dealing with intersection yet today, I don't think. So, or the union. So A or, this means A or B. Anytime you write it down on your paper, I don't care if you write it in words or you write that, but I might give you a problem like this and you have to know what it means to be able to do the problem. So, for mutually exclusive events, probability of A or B equals what? Probability of A for not mutually exclusive events, probability of A or B equals what? What's different?
Probability of A plus probability of B minus probability of A.
And it's going to end up being the one that's intersection, but I still think I'm going to get it at the end today. And just because you might see it, a probability table or probability model, in the dice example, what were my different possible outcomes for what color the dice could be? And so let's just leave these out of 12. I think blue was 6 out of 12. Well, was green 2 out of 12?
Green was 2 and red was 4.
And that was because of the actual numbers, not because I just so happened to get those same numbers. So like if I say draw a probability table, that's what I mean.
Wait, so you just did the ones that you drew, or
No, those are your actual probabilities.
not the ones that we drew?
Right, it just so happened that none were the same. Just so happened that I was awesome.
Do you need to simplify this?
When I do it as a probability table, I don't because if something's missing. But if you do it as like an answer, like just an answer, then you will.
Okay.
But like because of the math, to see what's left, I'll leave them all to the same one so I don't have to like convert and then think converting and then unconvert. You can just convert once at the end. I'm going to split the video, but I'm going to do some practice stuff.